Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about the question bank related to distribution of shear stresses topic. So in this we will see how to attempt the question on distribution of shear stresses. So how they will give in examination related to this topic, the shear stress topic, we will see. So first of all, we will discuss about the course outcome. At the end of the course, students should be able to analyze the simple bending for illustrating the distribution of bending stresses across the sections beams under loading. So theory of simple bending already we have covered, and then distribution of bending stresses also we have covered in theory part, and across the sections section beams under loading. So after completion of this topic, students should be able to analyze all these things. So that is the main outcome of this topic. The question number 1. So they explain the shear stress distribution over an I section with sketches. So first of all, you have to explain the shear stress distribution. So what is the shear stress distribution? And then I section. So various sections are there. I section, Z section, C section, okay, T section. So but in this question, it has asked only I section. So for shear stress distribution over an I section. So how it will distribute the shear stress along throughout the section? How to explain with neat sketches. So now we will see the distribution of shearing stress over an I section. Consider a beam of an I section as shown in figure. So this is the I section beam. These two are flanges, flange 2 and flange 1. This is web. So the dimensions of the I section is, one is capital B, that is width of the flange, and small b, the width of the web, and then here the web thickness, the flange thickness T, and in neutral axis passes through its center of gravity. So from this neutral axis to the cross section of first planes, the new distance is y, and then the bottom portion below the neutral axis, below the section, that is d by 2. From neutral axis to top portion, that is d by 2, capital D by 2. So here conditions are there. If y greater than d by 2, what will happen? This y value is greater than d by 2 in this case. So we will see one by one the I section shown in figure, the B overall width of the section, and D is the overall depth of the section, and capital D, small d is the depth of the web, the small d depth of the web from here to here. Capital D is the depth of the total section, overall depth of the section, and small b thickness of web, and small t thickness of flange. So you know that the shear stress on a layer jk at a distance y from the neutral axis. So that is shear stress is equal to F into A y bar by IB. Already we have derived in a theory part. In theory part we have discussed about the shear stress on a layer jk at a distance phi from the neutral axis. That is shear force multiplied with A into y bar by I into B. Now we shall discuss two important cases. One is when y is greater than d by 2. And second case, when y is less than d by 2. So what will happen? First, y greater than d by 2. The y value is greater than d by 2. See, in this section shown, all dimensions from jk layer to neutral axis y. Now it means that y lies in the planes as shown in figure. So in this case, shaded area of the flange. So here exactly at jk. Whenever the y greater than d by 2. So d by 2 the value is less than the y. So now in this case shaded area of the flange, take A is equal to area B multiplied with d by 2 minus y. Capital B multiplied with d by 2 minus y. So this B and multiply with d by 2. And the minus from neutral axis to here, the y given. So that is depth from its neutral axis. So now y bar, calculate y plus of multiply d by 2 minus y. So the y bar value from neutral axis to from its center of gravity. So y plus half into d by 2 minus y. So now substituting values of this A, area and y from the above equations in our original equation of shear force. So this is the original equation of shear force. So in this force is common, and then A and y bar these values may vary. So the area calculated and y bar. So the distance neutral axis to from its center of gravity. So now A already calculated, B into d by 2 minus y, multiply with y bar, y plus of multiply with d by 2 minus y divided by IB. So f by 2a multiply with d square by 4 minus y square. To simplify this equation, after simplification, we will get f by 2a into d square by 4 minus y square. So thus, we see that the tau increases as y decreases. We also see that the variation of tau with respect to y is a parabolic curve. So at the upper edge of the planes, where y is equal to d by 2, the shear stress is 0, and at the lower edge, where y is equal to d by 2, The lower edge is d by 2 and the higher, the upper edge is capital D by 2. So now the shear stress equation F by 2a into d square by 4 minus small d by 2 whole square. The y value here substitute d by 2 whole square in the previous equation. So after simplification you will get F by 8 I into d square minus small d square. So F by 2i, simplify here, d square minus 4 minus d square by 4. So take common 1 by 4 here. So it becomes E by F by 8i into d square minus d square. So second case, when y is less than d by 2. So now in this case, see, the d by 2 is higher than the y value. Now calculate here area and y bar. Again substitute in shear force equation, shear stress equation. It means that y lies in the web as shown in figure. The y value, the neutral axis to here, this value lies in web portion. Already know web. This one is flange 1 and flange 2. But in previously, whenever the y is greater than the d by 2, the y lays in the flange portion. But in this case, the y lies in the web. Why? Because the y is less than d by 2. So remaining the values for entire section, the width is b and d by 2 and small b web portion. So now calculate ay. So the b into d by 2 minus d by 2 here, and then y value is small d by 2 plus half multiply with d by 2 minus small d by 2. So simplify this equation. So b into capital D minus small d by 2 to 1 by 2 into d plus capital D plus small d by 2 after simplification of this equation. So finally we will get ay is equal to b d square minus small d square by 8. Now substitute in equation. So enter the value of ay for the web about jk. So the ay. So what is the ay value? Capital B into d square minus small d square by 8. So here shown the jk portion. From this edge to neutral axis is y. From neutral axis to the bottom portion of the flange, small d by 2, capital D by 2 already you know the total entire depth of the section. So now the total ay bar we want, and in the equation, the shear stress equation, force multiply with ay bar by ib. Force multiply with ay bar by ib. But we know ay, but ay bar need to calculate. The area is b multiply with, so d by 2 minus y. So the d by 2 minus y, the area. multiply with B, depth multiply with width, and then the y bar. Y plus half multiply with d by 2 minus 1. Now simplify this equation. B into d by 2 minus y multiply with 1 by 2 into d by 2 plus y. So now finally we got b by 2 d square by 4 minus y square. So now the ay bar, the y bar is calculated here. The total b into d square minus d square by 8 plus this y value, the center of gravity value y bar. So we'll get capital B into capital B multiply with this capital D square minus small d square by 8 plus b by 2 into small d square by 4 minus y. So you know the capital D, what is capital D and what is capital B and small d, small b. Now substituting the value of ay bar from the above equation, ay bar, in our original equation of shear stress on a layer at a distance y from the neutral axis. So thus, that is shear stress is equal to force multiply with ay bar by ib. So force multiply with the area capital B into small d square, capital D square minus small d square by 8 plus b by 2 into d square by 4 minus y square. Already we have calculated in a previous step. So this is ay bar. Capital B into capital D square minus small d square by 8 plus small b by 2 into small d square by 4 minus y square. So force multiplied with ay bar by ib. So the f by ib, take common, take outside here. So the remaining is b capital D square multiply with minus d square by 8 plus take outside here ib by 8 plus b by 2. So you can write here bd square by 8 minus by square by 2. So take LCM and then find out here bd square minus d square by 8 plus b by 2 to d square by 4 minus y square written. So otherwise you can keep like this. Then see that the web also, the tau increases as y decreases. We also see that the variation of tau with respect to y in the web also is a parabolic curve. At a neutral axis, y is equal to 0. The shear stress is maximum. So the maximum shear stress is F by IB into B by 8 into capital D square minus small d square plus BD square by 8. Why? Because here substitute y is equal to 0. So at neutral axis, the y is equal to 0. The shear stress is maximum. So that the shear stress at the junction of the top of the web and bottom of the planes, substituting y is equal to d by 2. Bottom of the planes and the top of the web. at a junction, top of the web, and then top of the web and bottom of the flange. So by IB, we multiply with the capital B by 8 into d square minus d square, substituting y is equal to d by 2. So here substitute here f by 8I multiply with b by, so already here written 8I, and then say here the equation rewrite f by 8I into capital B by small b into capital D square minus d square. After substituting y is equal to d by 2. So in this y is equal to d by 2, substitute in this place. Second case. So y is equal to d by 2. So d square by 4. So what will happen? The entire term will be 0. So here, note down 2-3 points. We see that the shear stress at the junction of the top of the web and the bottom of the flange is different from both the cases. We also see that the shear stress changes abruptly from f by 8I into capital D square, capital D square minus small d square to capital 8I into capital B by small b d square minus d square. So thus the shear stress at this junction suddenly increases by capital B by small b times shown in figure. See here in this figure, the shear stress at this junction suddenly increases capital B by small b. The shear stress increases at this junction. So here you may observe the shear stress at the junction of these two is different from both the cases, not uniform. So one case is y is greater than d by 2. Greater than d by 2, small d by 2 means the depth of the web portion. And the second case is y is less than the d by 2. See that your shear stress changes abruptly from this f by 8I into capital D square and small d square to this f by 8I into capital B by small b into d square minus d square. So already we have seen here. So in this case, substituting 0. In 0 case, f by IB into b by 8 into capital D square minus small d square plus bd square by 8. So in this equation, after substituting a d by 2, small d by 2, so you will get f by 8I into capital B by small b into capital D square minus small d square. So these changes happen. So thus the shear stress at this junction suddenly increases how many times? The capital B by small b times. So you can write this equation, capital B by small b multiply with f by 8I multiply with capital D square minus small d square. Capital B by small b. So the previous case, the shear stress is f by 8I into capital D square minus d square. Now, the second case, increase that b by capital B by small b times. What is b capital B? The total width of the web. Small b is width of the planes. Sorry. Width of the planes. And small b, width of the web. Width of that. So if the I section is symmetrical, the shear stress distribution diagram will also be symmetrical. Symmetrical about x-axis, symmetrical about y-axis. If the I section is given like that, the symmetrical section, the stress diagram also symmetrical. So that is the important point in this I section. So like this, how to attempt the question. So the distribution of shearing stress over an I section. So here we have taken I section. You may explain for another section, T section, same method how to follow. So like this, how to write the answer for the given question. So these are the references I have taken. Ramamurtham. Title of the book is Strength of Materials and Dhanpati Rai Publishing Company. And R.K. Bansal, a textbook of Strength of Materials. Publishers are Lakshmi Publications. And third book is R.S. Kurmi and Gupta. The title of the book is Strength of Material. And publishers are Chand and Co. So these are the references I have taken for this PPT, for preparing the question bank PPT. So take any one reference for further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.